so that we have, I still have to upload the recording from yesterday, but I checked and everything apparently went fine. So that's great. Yes, we are recording. Um, Good morning, everyone. Welcome to the second session of the data visualization for researchers course. Um, Another 3-hour marathon session, but when we're through this, we're halfway through the course. So that would be great. And also when we're through this, it's nearly weekend. So um, all is well there also, I think. So the session for today is the second session, and today will be maybe me. Oh, wow. Talking is going so well this morning. So last session was a little bit about the basics, the design basics and the communication basics and storytelling basics. Today will be a more theoretical session about graphic representation, whatever that might be. And the third session next week will be a very practical session with a lot of tools and techniques. Just as a reminder, come on, PowerPoint, work with me. Yes. So just as a reminder, if you have to, for one reason or the other, your concentration goes away, you stop listening to me, you miss something, part of the presentation, everything, all the slides that I'm presenting here and all the links that I'm talking about, all to the tools and to the inspirational examples, etc., can be found on my website. So if you need information about the homework assignments, etc., you can find it there. Also, the presentation slides should be on Moodle. I think I already uploaded the slides for presentation last Wednesday to Moodle. And as soon as this session is over, I will also upload the slides for this session there. And if there's any problem, just let me know. My email address is also on there. I think it's koen@barion.be. So as I said, the second session, graphic representation, 3 hours today. And then there are 2 more sessions next week. And don't forget that there will be a homework assignment that we will discuss together in the final session next Friday. So it should be ready by next Friday, 9 a.m. That would be perfect. Otherwise, it will be a little bit difficult to discuss, of course. So for today, graphic representation, what's it all about? We're going to talk today about how we can turn, if we have a bunch of data, if we have a bunch of complex information, how we can link this to certain visual variables, to certain design aspects in such a way that we can turn this data into something visual. And then we will have a look at a wide range of different chart types, and I will point you to websites where you can find even more types of charts and even more details about how these types of charts work. And then for each of these chart types, we will have a look at how we how these chart types work to turn data, to link it to certain visual variables, to turn it into a data visualization. Now it all sounds a little bit abstract and a little bit theoretical, but as soon as we have a look at the different visual variables and walk through them, I hope it will become a little bit more clear. And then finally, we'll have we'll talk a little bit about maps and about tables, because you don't always have to use a chart. Sometimes you can use a table just as well to convey the message that you're trying to convey to your audience. So we'll talk a little bit about table design. And finally, I will give you lots of inspirations, inspirational websites and books and blogs and videos, things like that. If you have some free time this afternoon, during the weekend, or later in your life, and you want to learn a bit more about data visualization or just be inspired a little bit more, then I will give you some places where you can go. So let's start with maybe the most theoretical part, which is called encoding. So we're going to encode data into something visual in order to make a data visualization out of it. We should grab back to the 7 visual variables. Now this is a little bit embarrassing because I forgot the name of the guy who who invented it. Well, invented is not really the right word, but who wrote this down and who ordered these different visual variables into 7 classes. But there are 7 ways how we can link data to certain visual aspects of visual objects. And so 7 main ways how we can turn data into something visual. And these are summarized in this visual. On top, for example, we will go through them one by one, but on top, for example, you see the size. So the size of an object can be linked to the data aspects, or the value of the object. Is it dark or is it light? At the center, you can see the position. So the two-dimensional position of the object can also be linked to the data information inside it. So for example, the first one, size, I always try to combine it, the visual variable at the left with an example at the right side, but there are hundreds and hundreds of different kinds of examples that you could make. But for example, this map, which is called a bubble map, because the data is represented as bubbles, is an example of how we are encoding our data through size, through the size visual variable. And why is that? Because the size of the circles, obviously, here is directly related to the number, to the data, so to the number behind it. So size is here the key visual variable which is used to turn the data into something visual. Just one note, obviously, if you're trying to reproduce this, or if you're trying to do this kind of thing, if you are using size as a variable, be aware that we are talking about area here, so that we are scaling quadratically, so to speak. So just don't directly relate your data to the radius of the circle, for example, but relate it to the area, which is proportional to the square of the radius, obviously. Otherwise, you will get some kind of distorted results where the size of the circle will quickly grow out of control. But be aware of that. But you're all scientists, so I think that will not really be a problem. So this, for example, is a great example of where we are. And this is, I think, the simplest way of how we can turn data into something visual is by just taking objects and scaling their size depending on the underlying data. It's the same principle is applied in a bar chart, for example, where the length of the different bars is directly related to the data. That's a first important visual variable. A second visual variable of the 7 is the value. So value, if you're not really familiar with this, it's a concept from color theory. If you're not really familiar with it, it means the intensity of the color. Not really the intensity, but if you have whether you have a very light color, which is closely related to white, or if you have a very dark color, which is closely related to black. It's clear, I think, if you look at the map, which is called a choropleth map, where each of the different regions here in China, in this case, gets a different, they all have the same color, technically speaking, but these colors have a different value. So in the West, in Xinjiang and in Qinghai, my Chinese is not that great, but there the value is very light of the colors. So we have very light, very desaturated colors, which are almost close to white, and our brain automatically interprets it as here the value is low. And indeed, if you have a look at the legend, it corresponds with these colors with a very bright color, or also where there are very little cases. In this case, unfortunately, it's another coronavirus visual. My apologies, but they are just very useful to explain some concepts. And in Hubei province, where Wuhan is, there we have a very dark color. So the color is always red, but here the value is very dark, meaning that there's a lot of cases there. So linking the data to the value of color is something that works very well, especially, for example, in maps of this type. Third visual variable that we can use in data visualization is shape. I think that speaks for itself. It's not something that you commonly encounter in a data visualization. I try to think of different examples where the shape of an object is related to the underlying data. It's definitely something that it's not impossible, but you will rarely encounter it where the data, where the shape is related to an underlying continuous variable, but usually the shape is related to a categorical value, underlying variable. So a variable which has certain discrete possible values. For example, in the example here on the right, you have a different shape if the data is talking about people, if it's cows, if it's pigs, or if it's sheep, and then for each of these 4 distinct categories, there's a different shape used in the data visualization. I must admit that I have seen another example once where the data visualizer was using, for example, a pointy star shape, like you can see on the very left of the image on the left. There's a very pointy shape, and then depending on the data, if the data was, for example, very high, then the shape would be very pointy, and if the data was low, then the shape would not be pointy at all. It would be more like a circle, and so in that way, you could always also relate a non-categorical data variable to a visual variable, but that's something that's really quite rare. If you see a shape linked to a data, then it's usually categorical data, which has just a few discrete values, like in the example on the right. The next visual variable is orientation. So when you have the same shape, but it's just oriented in a different way, so it can be positioned. For example, if you have a line, or so in the image on the left, it's we have rectangles with a different orientation. In the example on the right, we have lines with a different orientation. We can have horizontal lines, we can have vertical lines, and everything in between. And it turns out that this works pretty well because our brain tends to be very good at comparing different orientations with each other of lines. So the graph, which you can see on the right, is called a slope graph, where we are comparing 2 different points in time with each other, and we connect these data points with a line. So the slope of the line between them immediately tells us something about how the data is evolving. So the dark line on the top, for example, the popularity of people of football, so people watching football. We're talking here in the United States, so it's American football is declining. We can immediately see that this line is going down. And on the other hand, the green line at the bottom, which is soccer, so real football, so to speak. So soccer is going up quite dramatically. From 2 to 7%, the popularity. And our brain is apparently very good at comparing these different slopes. And that's why a slope graph, of which this is an example, works pretty well as a data visualization. Then we have color. I think that's the 5th one. So the 5th visual variable is color. This speaks for itself, I think, where we are simply relating the underlying data to specific colors. There's a lot, really a lot, and I think we're coming back on this in next session, that can be said on how should we link the data to the certain colors. You can, for example, have a 1 color scheme or a 2 color scheme or a rainbow color scheme. And depending on the data that you want to show and the message that you want to share with your audience, you will have to choose a different type of color scheme. In the example here on the right, it's pretty simple because we have, again, categorical data. So with certain discrete values, in this case, the different political parties that exist in Belgium, and each political party is assigned a certain color. And then on the map, just the districts or the the cities where this political party has reached the majority, they are colored according to the color that they were assigned in the legend. So it's a discrete color scheme, and that usually works pretty well for this kind of categorical data. I think that speaks for itself. And then the sixth one is position. So we have had shape, value, orientation, size, a color, and now the position. And position is something, especially two-dimensional position, which is used in data visualization. And I think a very obvious example is a scatter plot, where we're looking at two parameters of the data, and one parameter will be linked to one dimension of the two-dimensional positioning, and the other parameter will link to the second dimension of the two-dimensional positioning. And in this way, we get laid out in a rectangle the positions of these different, in this case, it are countries. So each country has certain characteristics. In this case, we're looking at the income, and we have put the income, the average income of the average person living in this country. We have put it on the horizontal axis, so on the x-axis, and on the y-axis, we have put the lifespan, the life expectancy of an average person living in these countries. We have put that on the y-axis. And if we do that, every country gets a certain position in this scatter plot. And this one, which was done by Hans Rosling, I think, or by Gapminder, which is the company founded by Hans Rosling. Note that he has also included some other visual variables. So size, for example, so the first one that we saw. So each data point is also scaled. It's a bubble which has been scaled according to the number of people living in those countries. So that's why India and China are so very large, USA as well. Probably if you would be looking for Luxembourg, it would be a little bit difficult to find. Oh, it's on very top right. So people are very rich and live very long in Luxembourg, but there are not a lot of people. And then a final visual variable which has been used here is the color. So each of these countries, each of these bubbles has been colored, and that's simply by the continent that they are in. So the red ones are in Asia, the blue ones are in Africa, green is the Americas, etc. So there are, in fact, 3 different visual variables used in this single scatter plot, but the main one, I think, is the two-dimensional positioning, and then we have the size and we have the color. And finally, the 7th one, I think, is rarely used in data visualization, but it is a possibility. You could have different textures, and make a distinction between different data using different textures. But it's a pretty difficult thing to do and to do well. But I have managed to find an example of a data visualization. In this case, a donut chart. Using different textures for the different data categories, but it's really quite uncommon. That doesn't mean, of course, that it's not possible. So those were the seven visual variables that we can link our data parameters to, and then try to see if we can create a data visualization by linking the data to these 7 visual variables. And then using these links that we have created between the data and the visual variables, we can try to start representing what we want to represent in different ways. And then there are, well, I have listed 7, just like the last Wednesday we saw with the design principles. Different people will have different ways of categorizing these ways of graphic representation. I have chosen 6, which are in my mind pretty straightforward or a pretty straightforward way of categorizing it, but you will find people who have 7 categories or maybe fewer categories and then with subcategories. Sometimes gets a little bit complicated, but don't worry too much about it. Don't break your head about it. It's just we're trying to approach this in an analytical way, how we are creating data visualizations, but exactly how we are doing it is not always the most important thing. It's whether it works or not. But the most common one, and I think especially for what you will be doing or what we are doing as researchers when we are communicating about our work, when we're communicating our research data, a lot of times we want to make a comparison between different categories, or a comparison, between different groups of the data. And in that case, we can, for example, use, like on the right side, I have put an example, in this case, a bar chart. So in a bar chart, we are trying to make a comparison between different categories. That's the category of graphic representation that we're doing, and the visual variable that we're using to make this comparison is, in this case, size, because the size of the rectangle, the size of the bar, says something about the underlying data. So the size of the top bar in this example is linked to the underlying data point 43, and the size of the gray bar at the bottom is linked to the underlying data 31. So their size, in this case, their length mainly, is scaled to the underlying data. So it's very, if you look at it, it's very basic and very simple to understand. If we try to talk about it in a highly analytical way, it sounds a bit abstract and complicated, but it could help us to build a theoretical framework about it if you would like to have that. Distribution is something else, or where we're not really comparing between different categories, but where we are looking at a more a continuous parameter or a continuous variable, and we want to see how the data points are distributed among these this continuous variable. And then a histogram, for example, or maybe a line chart are better options to visualize this such a distribution. But we will see more examples of this later when we are looking at the different chart types. Correlation is somewhat related to distribution, of course, because we're usually looking at two continuous variables simultaneously. But by plotting them in a scatter plot, for example, in this case, we want to find out if there is a correlation between the two. So if one parameter or one variable is changing, does the other variable also change, and does it change in the same direction, or does it change in the other direction? So do we have a positive correlation or do we have a negative correlation? And if we want to do correlations, then we should look at usually at scatter plots. So if we're talking again about visual variables, we will be talking about usually the position visual variables to see if there is actually a correlation going on or not. Sometimes we want to show, or we want to find out if there's an underlying hierarchy in the data. And then you have specific chart types that you can start using to show hierarchy. So where certain categories are the parent of certain subcategories, or which subcategories together belong to which parent categories, and things like that, and how large these different categories are, or how many data points are within each of these categories, how are they all linked together. Then you can make certain types of data visualizations. For example, this is called a sunburst chart, which is used to show, well, to group certain subcategories together. It works best if this is in an interactive version, so you can start clicking on the different rings and start exploring what's beneath this. But this is to give you in a bird's eye view an overview of CO2 emissions, I think in this case, of all the countries in the world. And then by grouping them you can see, I'm sorry, you can get a better view, and then you can start exploring further and deeper if you want to, if by looking at the outer rings. So if we want to show a hierarchy, we need to have a look at this kind of specific chart types. Evolution is another logical one, which is different from simply comparing or from simply looking at the distribution. If we have an evolution, then one of the parameters is typically time, and then we want to see how another parameter or another variable is changing as time is progressing. And I have included again another simple example of a visual which I created showing how the oil price has been changing over the past few years. And this is the oil price at the pump here in Belgium, by the way. And you can see what fraction of the oil the oil price at the pump is coming from taxes, and what price is actually coming from the price of the raw oil, which is behind it. So showing evolution is another way of, or another category of graphic representation that we can do. And then finally, because it doesn't really fit in any of the other 5 categories, is spatial graphic representation, where the data is directly related to specific locations, and then obviously maps will be the way to go if we want to visualize this. You could say that that again, this is a kind of using position as a visual variable, which is true. Wow, I'm sorry, I lost track a little bit. But here in this map, for example, you're using position as a visual variable, and it's linked also with color. And you can see that the colors also have different values. So again, there are 3 different visual variables used and combined in this single data visualization in order to also show 3 different underlying parameters: the country or the region within the country, whether the value is positive or negative, and whether the value is high or low. So 3 different visual variables here are used to show 3 different things, of which spatial graphic representation is one of the categories. Wow, I'm really sorry, because that's you can probably notice at the way that I'm talking about it. For me, this is a little bit too theoretical. I prefer to just create data visuals and see what works best and what doesn't work. But if you want to analytically find out why a certain data visual works well and then another data visual doesn't work, it's usually related to what things are we trying to represent. So what properties are we trying to represent? Is it, do we want to make a comparison? Do we want to show a distribution? Do we want to show a hierarchy? And then actually making a choice. Usually this is a very unconscious choice, but if you want, you can make a very conscious choice. Which visual variable are we going to use to turn this specific thing that we want to represent into something visual? Are we going to link it to the size? Are we going to link it to the shape? Are we going to link it to the value, etc.? So 7 visual variables, 6 different categories of graphic representation. To make it a little bit more practical and maybe a little bit more fun, I have a small exercise for you. This is a famous exercise within data visualization field. And we're going to look at a data set, but the data set is extremely minimal. So we just have 2 data points, and we don't know anything about the context. We don't know what these numbers represent, but we know that we have 2 numbers, namely 75 on the one hand and 37 on the other hand. And what I would like to ask you is to take a piece of paper and take a pen or a pencil and try to come up with some ways how you would visualize this data set. So just to fix your mind a little bit, one example could be we we will draw two rectangles, one with area 75 and one with area 37. That would be one way of visually representing this two-number data set. Then we have a small rectangle and a large rectangle. Or for example, you could create a pie chart where one slice is related to 75, so will be bigger, and one slice will be smaller because it is related to the number 37. But please let yourself go. Think out of the box. Try to come up with different ways to represent this two-number data set. I have listed again the 7 visual variables. So if you want to work with pointiness, if you want to work with different colors, if you want to work with position, feel free to write down whatever comes up in your mind. Let's say we will take 10-15 minutes to do so. If there are the first thing to pop up in your mind will probably be the very obvious ones and the very basic ones. Just write them down so that they're out of your head, and then try to think of more exotic ways or maybe more out of the box ways to start visualizing this two-number data set. And then afterwards, we will have a look at what other people have done, how they have approached this problem, and ways they have found to visualize this two-number data sets. So take a piece of paper and a pen, and we'll see each other again in 10 to 15 minutes. Okay, so we're back. Before we go into the answers that other people gave on this question, we have a question in the chat by Dimitri about the map, which I showed a few slides earlier, just one slide earlier. Why Lithuania and probably the other Baltic countries are so, or they appear so oversized compared to Poland. I have taken a look at the map and I completely agree. I think there are two main reasons. First of all, I looked up what the different areas of these countries are. So Lithuania, the area size of Lithuania, which is just to the northeast of Poland, is about 1/5 of the area of Poland itself. I think part of the reason here is the map projection which has been used, which causes a little bit of distortion, maybe because Lithuania is more to the north than Poland, or maybe because it's more to the edges of the map compared to Poland, depending on specifically which kind of projection is used here, and I'm not sure about that. Secondly, and mainly, I think, and that's actually quite interesting to talk about here, is that the value of the red color. So Lithuania is very dark red, and Poland, all the different regions in Poland, they are very light. They are quite desaturated colors. So there's a very large value difference going on here, and to our brain, yeah, we are automatically attracted to the very dark regions. That's one, and also to red as a color, because historically or evolutionary, we have to be cautious of things which are red, and that's why warning signs are also red, etc. So our brain is wired to look at this dark red color and to probably overestimate it compared to the very low saturated colors of the different regions in Poland. So that's something, yeah, I think that's quite interesting, and it shows. It's one of the reasons why I'm not really a fan of these kinds of maps. There are different reasons why I think these kind of choropleth maps, sorry, are not always very suited for data visualizations. You see them a lot, especially, for example, with numbers of corona infections. But I don't really like them for this reason, because it's difficult to compare different regions with each other, or difficult to compare colors of different regions with each other. That's one part. And secondly, because it's just very difficult to see what's going on in very small regions. Like, for example, Luxembourg. You will probably be interested in Luxembourg, but if you have a look at a choropleth map, Luxembourg is simply very small. Or if we, and this is simply just a map of Central Europe. If we have a map of the world, for example, and we want to know how many corona cases there are in Singapore. Singapore is also insanely small, so it's completely impossible to see on a world map how many cases there are in Singapore. In that case, I think a kind of bubble map, let me go back, kind of map like this works a lot better, because here each country has its own bubble, and it doesn't depend on the size of the country in question. And for that reason, I would prefer this kind of bubble map compared to, or I think this works much better than a choropleth map, where each region gets its own color, for these two reasons. And as Dimitri correctly says, Germany also, well, Germany has also larger territory than Poland. So yeah, so I think what they did here is to use a kind of central projection, where with a center point somewhere around Luxembourg, and then all the countries near the edge of the map. So here in particular, it's obvious for the Baltic countries, they will be very distorted, because they will be near the edge of the map. They will be a pair larger than they are. But that's maps, and maps was actually for the last part of this session. So we will get back to it. So our two-number data set, 75 and 37. How can we turn it into something visual? So this is a famous exercise that a professor in I don't know where always does, and he has summarized the responses of his students, and he also tried to categorize it a little bit. So a few of the things that I already mentioned as a first ID, this is only one part. He has 45 different kinds of solutions, but to visualize data set, these are maybe the more standard ones. So for example, we have in number 5, we have what is typically a bar chart, where we are looking at two bars, and the length of the bar or the length of the line is related to 75 or to 37. So we have something more classical. And number 13 is what I also mentioned, is, for example, a pie chart with two slices, and one slice is smaller, which is the 37 slice, and one slice is bigger, which is the 75 slice. And you have different variations of that. For example, in number 8, you have two bars placed next to each other. In number 1 is simply writing down the numbers, which is also a way of representing the data set. It's maybe the most boring way, but technically it's also a way. Number 2 is also one of the basic ways, which is just on one hand drawing 75 small figures, and on the other hand drawing 37 small figures, so that we are representing 75 and 37 just by the number of shapes that are present in the data visual. Number 4 is maybe also interesting, where we have, so to represent 75, we take 7 large shapes and 5 smaller shapes. And then to represent 37, we have 3 large shapes and 7 smaller shapes. That's a different approach to, it's a little bit easier than drawing 75 shapes, and it's also easier to interpret if we want to interpret, or if we want our viewers to interpret this data set. You have some different kinds of further examples, especially the column on the right, where we take a shape and then scale it. So we really use size here as a variable to visualize 75 and 37. These are the more, how to say, the more basic or the more expected solutions. Then if we go to further solutions, here we have, for example, different kinds of shapes that we can scale, that we can make bigger or larger. We can use a clock or a scale to represent 75 and 37. So in 27b, for example, we have two scales, and 75 will be represented by a scale which is pushed down further and where the needle is pointing to a larger weight, and 37, in that case, the scale is pushed down less far, and the needle is pointing to a lower value. In 28, we have value used as a visual variable. So we have a dark square and a light square, and one is 75 and the other is 37. And in 29, for example, we have color used as visual variable. See that Dimitri is having to leave us for a little bit. That's no problem. See you soon, Dimitri. And if you need the presentation, you can download it afterwards. And some other examples. One that I really like personally is 39. I think that's quite original. I would have never come up with it anyway. So 39 is a representation where we have 75 dots and 37 connections between the dots. So one data point is represented here as dots, and the other data point is represented as lines between the dots. I think that's pretty cool, and people start thinking out of the box, start combining sine waves with different frequencies. Or number 44, they think conceptually, what if we generate two sounds, one sound with 75 hertz and one sound with 37 hertz, and then this is a kind of representation of our data set. It's not a visualization anymore, but it's a, how would you call it, a data sonification. But that's a different way to turn raw data into something, into something else actually, which was the point of everything that we have been talking about before. And 38, maybe final one to mention. 38 is an example of using texture as a visual variable. So the first one representing 75 has a quite how do you describe it? A dense texture. So the cross lines here are close to each other, and 37 has a bit of a lighter texture, of a smoother texture, because the lines are a little bit further away from each other. So if you want to use texture as visual variable, that would be, for example, a solution. Okay, enough with the very theoretical stuff. Let's look at more real-life examples and how they work and why they work and why sometimes they don't work. I think, well, at least for me personally, I'm talking myself down now, but that's more interesting than what we were doing before. So for the chart types, we can of course not skip the very common chart type. So this will sound pretty basic, but I think it's very interesting to analyze how these charts actually work and why they work and when they do work and when they don't work. So bar chart is like your default chart that you can always fall back upon, and that works well in like 90% of the cases. A bar chart will work very well for the data that you're trying to represent. So don't worry also if you're struggling with time, for example, to represent your data, or you're struggling with something very complex and you're not sure how to make it as clear as possible to your audience. Don't be ashamed to simply use a bar chart. It's a bit boring, it's a bit bland, but it's usually works. It's usually the best choice to represent the data, especially if you want to make a comparison. So that's why I wrote there, a bar chart is actually using size as a visual variable to make comparison. So the graphic representation that we're trying to do is a comparison, and we have chosen size as a visual variable. And then um, we get a bar chart like this. Some minor tips about creating a bar chart. If you have long category names, and that's quite often the case, I would advise you to use a horizontal bar chart compared to a vertical bar chart. A vertical bar chart is maybe a little bit more default, but it's making it difficult for yourself often, especially when you have long category names like here, for example. So on the left, you have to tilt almost break your neck a little bit in order to read the category names. And if you create a horizontal bar chart like on the right, it's, in my opinion, much easier to read. You also have a little bit more breathing space to show the data and to show the length of the bars. So usually if you have the ability to choose between a horizontal or a vertical bar chart, my personal preference always goes to a horizontal bar chart, but that's just a little tip. But in this way, we make it easier for our viewer. And as we saw on Wednesday, if we make it easier for our viewer to interpret what's going on and to read what's going on, we're actually taking away noise. So you could say that the left visual is a little bit noisy because people have to do certain kinds of things. They have to tilt their head, and there's also little spacing. So there's some noise going on that we have removed in the horizontal bar chart on the right. There are, of course, some pitfalls that you should avoid if you're creating a bar chart. An obvious one, I think, is if you're using a bar chart, make sure that your y-axis is starting from 0. So here's an example where on the left, the y-axis is not starting from 0, and on the right, it is starting from 0. And you can see that it's a way that people will often use to over-exaggerate differences between different categories. So as we are making a comparison basically with a bar chart, and people want or sometimes inclined to over-exaggerate differences between different categories, but that's not something that you should do. It's cheating a little bit because we are using here size, and with our theoretical framework, we can also explain why this is. We are using size here as a visual variable. And if you're cutting off a large part of these bars, you cannot accurately compare anymore the size between these different shapes, between these different rectangles in this case. And you get a much more honest picture if you are making the comparison like it's done on the right side, where each of the bars are starting at 0. And then maybe the conclusion is a little bit less spectacular, but then depending on the message that you want to share, if you really want to share that, actually the difference is not that much, so we don't care a lot, then you could easily use the bar chart on the right. If you really want to talk about the differences between these different, in this case, internet browsers and their power consumption, if you really want to talk about that and highlight that, you can of course definitely do that, but then don't use a bar chart to do so. Use an alternative. I think I have an alternative on the next slide. Yeah. Wait, I just have to open up there. So this is an alternative, for example, if you really want to highlight the differences between the different categories, but the differences are actually pretty small compared to the total number, then you can use what's called a dot plot, for example, rather than a bar chart. Now, this is a dot plot here, where we are looking at the men's long jump records, so the distance in athletics competitions that men can jump. And then obviously, yeah, because people around the world are very similar, for these different countries, there will be very little difference between these different values. So it's not like people in China will jump 6 meters and people in India will jump 12 meters. There will always be the differences between these different values, between these different categories, will always be very small. But that doesn't mean that we're not interested in them and that we don't want to visualize these differences. But as we have seen, a bar chart is not a good choice for that because we're using size as a visual variable, and that's we run into problems with that. But that switch to a different visual variable, and in a dot plot, we are actually using position as a visual variable. So there's no size differences between these different categories. There's just position differences. So there's one dot for each category, and it's positioned differently along the line depending on the underlying data. And that makes it easy to compare different values. So we can immediately see that in the United States, I don't know if these are real or imaginary numbers, but not really important here, but we can immediately see that in the United States, the long jump record is the farthest and it's almost 9 meters. And in Indonesia, it's the shortest and it's below 8 meters. So even though the differences between these categories are small, we have found a way to visualize it and to make it easy to compare without resorting to a bar chart, because that wouldn't work in this case. Another pitfall with bar charts that you sometimes see is if you are using it for evolution data. For using evolution data, the ground rule is it's usually better to just use a line chart. But if you really would like to resort to a bar chart to showing data which is evolving over time, then you have to make sure that if your labels are not equidistant or your data points are not equidistant, then your labels should also not be equidistant. This is an example, for example. Wow, I'm saying example a lot, so really sorry. Please don't start a drinking game where you take a shot every time I say example, because otherwise by the end of the session, you will be completely hammered. But this example is about the number of passengers at Brussels Airport. And if you look at the data labels, so at the different categories here, at the start, in the early years, there's always 5 years between the data. So 2000, 2005, 2010, 2015. But then starting in 2015, there's only 1 year between different data points. So making a comparison between the sizes of these bars, even though it's valuable, and luckily they'll also start from 0. So making a comparison is possible, but it's definitely distorted because it looks like maybe evolution has become, or the change in the number of passengers has become smaller over the years. But you can't say that because in the beginning there's 5 years between each data point, and now there's 1 year between each data point. So two solutions here would be, for example, to increase the spacing between the first bars to clearly show that there's more years between the different data points, or go to a line chart. And again, there, of course, you have to increase the spacing between the data points to show how much time has actually passed. But this is something that you will sometimes encounter, and that's actually not a great practice for a bar chart. Yeah, so if we're looking at data points over time, then a line chart is usually the better choice. Because here, for a line chart, we want to have a graphic representation of evolution, so how data is evolving. And we're using, in this case, we're using position to show how it is evolving. So the position of the line is telling us something about the data. You could also argue that we are using orientation to highlight the evolution, and that indicates how we are actually working in a gray zone here if we try to approach it analytically and build a theoretical framework about it. Orientation also plays a key role here because, as I said, our brain is so good at comparing lines and see when lines are going down and when lines are going up. So orientation plays an important role in creating line charts. For example, this line chart showing, sorry that this animation is going on and on and on, but it shows how Android has taken over the smartphone operating system market share. And even though people thought Nokia would win this, but Nokia has completely gone to 0 by 2013. So to show this, a line chart is a great option. A pitfall or a problem that you can have with line graphs is if you want to compare many lines together, and then you get what some people would call a line graph spaghetti, where it starts to become difficult to actually see what's going on. So this is popularity of baby names, and I would have to count, but 5, 6, Right, 12 different lines going on here, and if you want to see what's going on or what baby names were popular at what point in time. You have to constantly switch between the legends. Oh, which color is that name? Oh, that's a little bit, is that kind of green? Okay, where is the line for that kind of green going? So it takes a lot of time and it takes a lot of effort to see what's actually going on and to extract the information that you want to extract from this graph. And the best way to avoid this kind of line graph spaghetti is to think back about what we said last Wednesday. Actually, we take a step back and we think about, okay, what's the message that we want to share with our audience? Do we want to focus maybe on one specific name, and then highlight, make sure to remove some noise by removing, for example, the colors of the other lines, and highlight one specific line that we really want to talk about? Or we can cheat a little bit and we can make many what is called a small multiple approach, where we simply make, if you have 12 different names, we can make 12 different small charts. And in each case, we highlight one specific graph for one specific name, and all the other lines, we make them a little bit gray. So they're still there. We can still make the comparison, but they are pushed to the background. We have removed some noise to make the interpretation much easier. And then it takes up a little bit more space, but it makes it so much easier to immediately see what's going on and to extract the information that you want to extract from it. This is if you want to make a comparison possible between all of the 12 different names. If, for example, you're simply interested in the name Linda, then of course you can just show 1/12 here of the total graph, just the part where we have highlighted the line for Linda, and then make all the other lines gray, because those other names, they don't really matter. They simply serve as a comparison. But that's a way to avoid what's called a line graph spaghetti. Pie charts. Well, I'm getting hungry here talking about spaghetti and pie charts. But okay, this is a pie chart. Well, technically, this is a donut chart because there's a hole taken out from the pie chart, but we stay in food-related data visualizations. This is a donut chart or a pie chart where we are actually, we're not really making a comparison. We're again using size as a visual variable, but we're not really making a comparison. We're actually looking at the distribution, because the total number, or the total fraction, always amounts to 100%. And then we're looking how the data is distributed within this 100% over a few different categories. So in this case, for example, we have 3 main categories, and then some people who didn't answer the survey, and we have a look at how the answers are distributed within these 3 categories. So this is a distribution rather than a comparison. And that's also, we'll come back to this in a few slides, but it's a reason why if you are doubting between a pie chart or a bar chart, then usually you have to think in your head, okay, am I trying to show a comparison, or am I trying to show a distribution? And if you're showing a distribution, then a pie chart can be a viable option. If you're trying to show a comparison, then usually a bar chart is a better choice. But many people are strongly opposed against using pie charts. Personally, I think they can work very well in certain situations, especially in a situation like this where you don't have a lot of categories, but it can, of course, sometimes go wrong. And those are things to avoid. An obvious thing that can go wrong is when the slices of your pie, when it doesn't add up to 100%. That's usually when you have survey results, for example, and people could answer or could cross out multiple answers on one question. Then, of course, if you sum up the different percentages, you will have more than 100%. So that's not something to put in a pie chart, because in a pie chart, the total always adds up to 100%. But if you have a survey question and people can only select one of the different options, then a pie chart is a possibility. If you have more, if there are multiple options possible, and so the total is more than 100%, then again, it starts to get boring, but just use a basic bar chart and show here, these are different possibilities, again, from a survey that people could select. And if you would add up all these different percentages, you will maybe arrive at 200%. So a pie chart would definitely not be a good option here. And also don't use a pie chart when you have too many categories. This is not wrong. Technically, the data here is correct, but it just makes it much more difficult to extract information from it. If you really want to use a pie chart and you have many categories, then an obvious approach that you can do is simply combine some of the categories together and categories which are less important. And that depends, of course, on the message that you're trying to tell. This is, for example, a pie chart about people, so tourists in Belgium. We have looked at all the different hotels and nights that tourists have stayed here, and we looked at the nationality of these tourists. Of course, there are hundreds of different possibilities for nationalities, and probably they are all also present in the data, but we don't really care about, we're not going to show all these hundreds of categories in the pie chart, because in this case, we don't really care about it. We can show the main categories, and then all the others, we just combine them into an other category and make it gray and include it in the pie chart, but not explicitly label it. And it doesn't matter, because here are messages that, oh, look, nearly 60% of people staying in Belgian hotels are actually Belgians. So people are also doing a lot of tourism within their own country. And then we can give a little bit extra information. What are the other popular countries or countries that people come from to Belgium? But we don't have to go into endless detail, because that would make the chart unreadable. And as I said before, if we want to do a comparison, rather than showing a distribution, then a pie chart is usually not really a great option. So this is, again, survey data. People could indicate if the company they're working for, do they work according to a waterfall approach, or do they work according to an agile approach? The details of this don't really matter here for the example, but there were, let me see, 2, 3, 6, 7 different options that people could choose from. They could select one answer. So a pie chart is a possible way to represent this data, but it becomes difficult to, in one blink of an eye, see, for example, okay, which slice is the biggest? Or is the light orange slice, is it bigger than the light blue slice? Or yeah, it's difficult to make a comparison. It's helped a little bit now because the actual values are there on the chart. So I have added some, remember, some effective redundancy here, but it's still difficult to quickly make this comparison. And again, it starts to be very boring, but if you want to make a comparison between different categories, simply use a bar chart. And if you look at the bar chart on the right, this is exactly the same data. But if I ask you the same questions like, okay, which category is the largest? Bam, it's category number 5. Or yeah, is category number 2 larger than category number 6? No, because category number 6 is just a little bit bigger than category number 2. So making comparisons is much easier if you're using a bar chart than a pie chart. And I think final pitfall that you can have if you're creating pie charts is that, especially if we're looking at very tiny fractions, so like the 2% here at the bottom, but it's a personal opinion, but I found it difficult to see these tiny slices or to get an impression of how much this actually is. You see a very tiny like slice. It's almost more like a line than a slice, and then you see the entire circle. But for me, it's difficult to estimate, is this a lot? Is this not a lot? It's difficult for me to draw a conclusion from that. This was work that I did for a client, and the client really insisted that we were using circles and not bar charts. So, okay, client is king, obviously, but I switched to another approach where instead of drawing a pie slice, I drew smaller circles within the larger circles to indicate these fractions and to make comparison a little bit easier. So the 2% represented as a circle compared to the larger green circle or bluish circle is a little bit easier, I think, to compare than the tiny pie size. This is a detail, but it's just a small tip if you're dealing with pie charts and dealing with very thin slices. Think about an alternative solution like this. And there is one final thing about pie charts, but I'm sure that you're all aware of it, that you're smart enough to never make this mistake. But please never, it applies actually to all different kinds of data visualizations. Avoid three-dimensional charts as much as possible, even though they look pretty, but they give a completely false impression about the underlying data. Because for it, take this example from a car advertisement. Of course, Hyundai wants to stress that the Hyundai Verna is the largest ones in its segment, but it's overestimated because we also see the side of the three-dimensional pie here, and this gives us extra yellow on the screen. But this side of the pie is not related to any part of the data. The data is only related to the size of the slice and not to the height of the pie. So the side of this pie is completely is distorting, or it's again, it's not wrong per se, but it's making it more difficult for the readers to accurately see what's going on and to accurately make comparisons. Again, you could just as easily make a bar chart, and even with a boring bar chart, it's clear that this Verna car, whatever it is, I don't know anything about cars, but is selling much better, nearly double the second largest category. So to me, this is obvious enough. So there are other possibilities to show this data rather than this fancy pie chart, which is lying a little bit. So a scatter plot is another of a very common chart type. I'm pretty sure that you will be using this already a lot in your PhD work. If you're writing an article or if you're making a poster presentation, scatter plots will be in there, so you know how to use them. I wanted to link it back to what we have said earlier. So in a scatter plot, we are looking at distribution in two different dimensions. Often we're also looking at correlation. So okay, I admit that this is a data visual from my own PhD, and I admit that the correlation is a little bit far-fetched, but if you know the theory behind it and the context, it really is there. It looks a little bit far-fetched, but it's actually not. That's okay. So we're trying to represent correlation and distribution in a graphical way, and we're using position, two-dimensional position, as a visual variable to do so. I wanted to talk a little bit about scatter plots. I'm sure that you all know how they work, but just because to introduce one of my favorite examples of all time of telling stories with data visualization. Let me get my book. That's the advantage of teaching from your living room, is that you can just go to your bookcase and take the book that you want to show. I don't know how well you can see the video of me, but this is the book Factfulness by Hans Rosling, which we already mentioned a little bit earlier in the scatter plot example. But Hans Rosling, who has unfortunately passed away a few years ago, he was a wonderful guy, and his mission was to show the world how great that we are all actually doing. So he wanted to introduce some positivity in the world. He had a very positive view on what's going on, and he used data visualization as a way to share his message. So obviously I have to love this guy, people who are using data visualization to share their message, and especially when it's such a positive, such an optimistic message. And this is an example. So here he's using a scatter plot. We're looking again at two different variables. On the horizontal axis, we have the number of babies per woman. So on the right, and it's going from high to low. So on the right, women are only having 2 to 3 babies during their lifetime on average, and on the left side, women are having 6 to 8 babies during their lifetime. And this is actually an indicator for how poor or how rich people actually are, because poor people will have usually a lot of children to help them later and to care for them when they grow older. Rich people will usually have less children because they need less support and things like that. And on the vertical axis, we have the child mortality. So again, at the bottom, we have, so we're actually showing the fraction of children surviving to age 5. So at the bottom, we have the countries with a very high child mortality, where a lot of children die before they reach the age of 5. And at the top, we have very low child mortality. So nearly 100% of children is surviving. And again, like in the previous scatter plot that we saw, each country has its own bubble. The bubbles are sized according to the number of people living in these countries. So the two very large bubbles that you see are India and China, probably, with almost 1 billion inhabitants. But so if we take each country and look at these two variables and then position them in this scatter plot according to child mortality and number of babies per woman, then we get this clear distinction between two groups, and the two groups that we know as the developed countries, where people have small families, so women have a small number of babies, only 2 or 3, and with very low child mortality. So nearly all the children survive until the age of 5 at least. And then we have the developing countries, so this large box on the left, where women have lots of babies and children survive, or the child mortality is a lot higher, unfortunately. And that's why many people in their heads have the belief that we live in two different groups in the world. We have the developed countries, where luckily we are a part of, and then we have the developing countries who are very poor and large families, etc. This is a narrative that many people believe in because they have learned it at school, and that this kind of data tends to show that pretty clearly. But the problem with that is, maybe the beautiful thing about this is actually data from 1965. So in the 1960s, when our parents were young, at least my parents, I don't know about your parents, but in the 1960s, this was the case. And then you had this really clear distinction. If you would look at the same data now, I think in 2017, yes, and you do the same exercise, so you look at the average number of babies per woman, and you look at the child mortality, and you plot it, you get a completely different image. And as you can see, again, in 1 second, you can see the point of this visual. Nearly all the countries now, or what we would call in the 60s, the developed countries. So we have very small families throughout the entire world almost, and we have very, very, very low child mortality, at least compared to the situation in 1965. There will always be a few countries still that need some help or work in lowering child mortality, and that we could consider as developing countries, but it's really those are really the outliers. Nearly all the countries now are what we would call developed countries. So this divide that exists in many people's heads between us, the developed countries, and them, the developing countries, it's actually completely not true. So this is. And that was an eye opener for me, and I like it because it's, first of all, it's using data visualization to tell a story, and secondly, because it's a very positive and optimistic story. And that's why I definitely wanted to include it in this session, even though probably you already know it, or you obviously already know how a scatter plot works. Now, that's enough talking for me, maybe for now. So I suggest that we take a little 15-minute break so that I can drink some tea and let my throat rest for a little bit. You can go stretch your legs, also have a drink, maybe go to the toilet if you need to. I suggest that we see each other again at 10:50. So it will be 17 minutes instead of 15 minutes. So we will see each other again at 10:50 or 10 minutes before 11. And then we will go to the second part and we will have a look at maybe a few more exotic chart types. These were the basic, very well-known chart types. And after the break, we will have a look at the more exotic chart types and some inspiration on where you can find more great exotic out-of-the-box examples. So see you at 10:50. Good, we are back. I have a fresh cup of coffee. Um, so we're ready for the second part of the show. We go back to the table of contents that we have here. So we have seen this very theoretical part about encoding and how to choose visual variables in order to do different types of graphic representation. And we have talked already a little bit about the common chart types with some examples and with some typical pitfalls that could occur. But a bar chart, a pie chart, a scatter plot, a line chart, they're all very nice. And I tell you, in 98% of the cases, it will be perfect choice. But maybe we will also want to have a look at some less common chart types. I still have to open up my second screen here. Okay. But the thing is, with these less common chart types, there are a lot of chart types. Believe me, there are chart types in the world that you have never heard of before, that I have never heard of before, even though I'm doing this for many years already. So my way to approach this, or something that I really like, or there exist websites where people are doing nothing else than simply collecting all the kind of chart types that exist. So for example, DataVis catalog is one of my go-to websites, and here you can see an overview of many of the different more exotic chart types that exist. Well, the basic ones are also in there, like a pie chart or a bar chart, but there are also more exotic ones that maybe you haven't heard of before. The Nightingale Rose chart is there on the bottom row, which we talked about Wednesday in the historic data visualization. So, or we can have a Marimekko chart, if you have ever heard about it, a violin plot, a radial column chart, much more. And what's really nice about it, this is not just a listing of different chart types, but if you go to DataVis catalog and you click on one of these chart types, you will immediately get an overview. For example, this is for a tree map. Imagine that you go there and click on the tree map chart type. You will get some visuals on how it looks like, what it's used for. So it's used for comparisons, also to show hierarchy between data, because we are in a tree map, different shapes are contained within bigger shapes, which are then the parent category of the initial category. There's a description of how it works and how this data transformation from data into something visual, how it actually works. You get some examples or some links to examples that you can explore. You get some similar charts, which is also sometimes interesting if you know, like, okay, I know that my data could be represented as a tree map, but I want to know some alternatives. Then you have some similar charts which can be used usually for the same or for a very similar purpose. And very importantly, on the right, you see a list of tools that you can use to generate a visualization. Because next session will go more into details about the practical approach to create data visualization. But there are so many tools out there, and like every week a new tool is popping up to create a new different kind of charts type to help you with that. Or you can use online software or offline software, or things that you already know or completely new software tools. There's so much approaches that you can use to create a data visualization. And it changes so rapidly that I cannot give you a comprehensive or an exhaustive overview. And then sites like this, like DataVis Catalog, will give you a list of different tools that you can use if you want to create this specific kind of visualization. There are alternatives to DataVis Catalog. For example, ChartMaker directory here on the site of Andy Kirk, site visualizingdata.com. Very interesting site with blog posts about data visualization, but we'll come back to that later. But here you have a list of different chart types. You again see the chart families in the legend at the top right. But Andy Kirk here uses a little bit a different approach than we did when we talked about the graphical representation categories. But you will still find, I think, your way in it. And then he is really looking at all the different tools that exist and which tool can you use to create this kind of chart. So for example, you will obviously have, it's not in here, but Microsoft Excel will, for example, also be in here. And then you will immediately have a list of all the different kinds of charts that you can create with the basic tool that you already know, like Excel. So ChartMaker this is very comprehensive, maybe even more comprehensive and complete than the DataVis catalog, with a little bit less intuitive and with a little bit less information about each of the chart types. And chart.guide is a third alternative, and they have a very nice poster if you want to have a large poster with different kinds of chart types to put on your wall as a kind of a cheat sheet or reminder. Then chart.guide is an alternative. So some of these more exotic chart types or chart types that are maybe a little bit less common, and I tried to select, this is just a very small selection. We're definitely not going to talk about all of them, but I selected 2 or 3 of them, and I tried to select some charts that are pretty easy to also start creating yourself. So for example, a waffle chart. I'm really getting hungry now. I should have taken something to eat during the break, but okay, that's my bad. So a waffle chart could be used as an alternative for a pie chart, because also we're looking at distribution over a total of 100%. But it's a bit, it's a different approach, and it's actually also easy to make. What we're doing is actually we're creating 100 small shapes. Well, for example, but in this case, it's 100 small circles. We put them next to each other in a 10 by 10 square, and then we simply color the different circles according to the category that they belong to. So we're rounding off, of course, to 1%, but usually, if depending on the message that we're trying to convey, this rounding off is not really a problem. And this works really well, this kind of waffle charts. I think if there is one category that we want to highlight, or one fraction that we want to highlight compared to the total of 100%. So here, and it's very easy to quickly see the message, like when we have a large fraction, when do we have a small fraction, and it's very easy to make because all we need is just 100 circles. That's quite easy to create. Another less common chart type is a strip chart, which is basically, it's like a scatter plot, but well, instead of 2 continuous dimensions, we have 1 continuous dimension. Here it's on the x-axis, and the other dimension, which is here on the y-axis, is a categorical or discrete variable. So in this case, there are 3 categories, 3 different kinds of sports. So the data is also, it's like 3 little scatter plots, but linear scatter plots combined into one, and it makes it quite easy to compare the different categories between each other, depending on the variable that you want to look at. Here it's a z-score, for a test to see if your muscles are more prone to, if you have very fast twitch muscle. This is detailed behind this chart and completely irrelevant, but I just like talking about it. So the green circles are for people with very fast twitch muscles, and that means that if you have fast twitch muscles, you will be very good at sprinting, for example. If you're a runner, you will be very good at 100-meter sprint. If you're a cyclist, you will be very good at the end sprint at the end of the of the of the tour, the episode of the tour. Wow, it's really difficult to find your words on a Friday morning. If you have slow twitch muscles, then you will be very good. If you're a runner, you will be a very good marathon runner. If you're a cyclist, you will be good in the mountains because you have to continuously give a lot of force or generate a lot of energy continuously over a longer amount of time. So you will be a very good climber in that case. And that's what you see, that if you look at the endurance sports, people who are very good at endurance sports will generally have a slow twitch typology if you start measuring their muscles. If you look at people who are very good at explosive sports, they will generally tend to have a very fast twitch typology. And in a football team, if you start scanning the muscles of people playing football, soccer actually, you will see a wide distribution of people. Some people will be very good at sprinting. Some people will be very good at running long distances. And so this is interesting for a coach to see, okay, who is better and who should I put in what position and who should I give what tasks, because depends on the muscle typology. Wow, this completely non-data visualization related talk is now over. Let's go to the next type of less common chart or not so very common chart type is a slope graph, which we already mentioned because our brain is so good at looking at different orientations of lines. So even here in this case, where there's actually not really a large difference between the orientations of the different lines, our brain is still very good at spotting the differences and at seeing that, yeah, the construction and packaging categories here, for example, are growing a little bit faster than the automotive or the footwear categories, and that the wood and furniture category is being completely stable. So we are comparing just 2 points in time in a slope graph. Actually, it's a kind of a line graph, but we're really focusing here on the orientation of the line by looking at simply 2 points in time and comparing these 2 points in time for different categories. So we're looking at orientation rather than position. And then a final less common chart type that I like to talk about is a Sankey diagram. It's a little bit more difficult to create, although there are online tools to create your own Sankey diagrams. But basically, the key concept in a Sankey diagram is that we are drawing arrows or drawing lines, and each line or arrow has a widthness, and the widthness corresponds to, so the widthness is basically the visual variable because it corresponds to the underlying data. For example, this is probably the most basic Sankey diagram that you could create. If you have 100 joules of energy going into a classical electrical light bulb, only 10% of that, so 10 joules, will come out as light energy, and the other 90% of the energy will be lost as heat. So here, this is visualized by having a white arrow, which is splitting in two, and only a very small arrow is coming out as light energy, and still a very wide arrow is coming out as heat energy. And the width of these arrows, so it's directly related to the underlying data. This is an extremely basic example of a Sankey diagram, but it's used commonly in more complicated cases to draw diagrams, for example, of how energy is produced and how it is consumed. In this case, in the United States, for example, and the width of the lines, you can immediately see that, oh, a lot of energy is produced. So the production is on the left. A lot of energy is produced through using natural gas or by burning oil. So the blue and the green lines are very wide, so are very present. And then you can see what these different kinds of energy are used for and how much of each type. And finally, you can see how much is used actually usefully and how much is lost in heat or through friction, etc. For example, so Sankey diagram in energy management is used quite a lot. But why I really want to include Sankey diagrams in this presentation is because there's a great example of a data visual using a Sankey diagram and a data visual that tells a really interesting story. Some of you might have already seen this data visual. In that case, sorry for the repetition, but I personally really like it and I like to explain what's going on. So this is, if you think that a Sankey diagram is something new, it's definitely not. This is a Sankey diagram from the 19th century, 1869, and created by Charles Minard, who was really one of the first to really create data visuals to tell things about economy, to tell things about historic events. He used bar charts and line graphs, basically introduced them. But in this case, he used a Sankey diagram, and he wanted to talk about Napoleon and the campaign that Napoleon was doing in order to invade Russia. So we have to start, if we want to read this data visual, we have to start at the left when Napoleon and his army are in Kovno. So we're looking at the brown arrow here, and the brown arrow there is still very wide because we have, I think, 422,000 soldiers when they were in Kovno, which is in the Baltics, if I'm not mistaken. And then as Napoleon is traveling east towards Moscow, what you can see is, so temperature is getting colder and colder as winter is coming, and the Russians are using their tactics of the scorched earth, so that Napoleon's army doesn't have any supplies anymore. And this brown arrow, is getting smaller and smaller and smaller in width. And by the time that the army arrives in Moscow at the right, you see that this line has become much thinner, and only 100,000 soldiers of the original 422,000 have actually managed to reach Moscow. And then they still had to turn back. So that's the black line when they are turning back towards the west. And you can see it's winter is still becoming stronger and stronger, and they are losing more and more men. You can also sometimes see the width of the line drastically decreasing when they are crossing a river. And by the time they arrived at the point where they started in Kovno, there are only 10,000 soldiers left. So we have a very thin line left, where they started with more than 400,000 and a very broad line. When they're coming back, it's a very thin line. So this Sankey diagram tells, I think, a fascinating historical story, and it's more than just showing the data, but also do some great storytelling. That was my last example of a less common data visualization. I will shut up again for something like 15 to 20 minutes. Let me look at the clock and what we still have to do. I think it will be around 20 minutes. Because it doesn't really work, of course, if I'm the only one just talking and showing you these different kind of chart types. I want you to get some feeling with it, and especially maybe chart types that you haven't heard of before or that you want to know more about. So these are the 3 websites that I mentioned, where you can find an overview of different chart types, information about how they work, and information about tools, how to create them. So take this time to browse around these websites. get familiar, learn something new, explore maybe some examples, because there are usually also links to different examples of data visualizations. And if you have any questions, just put them in the chat. If it are really very specific tool related questions, I'm not sure if I will be able to answer them, because I also don't know all the tools that exist to create the visuals. And we will talk a little bit more about the tools in the next session. But just if you have any questions, put it in the chat and I will see if I can answer it. We will answer it in the group together in about 20 minutes. So have some fun exploring, put your questions in the chat, and we will see each other again at 11:30. Okay, I'm back. I see that there aren't really any questions in the chat. If you still have a question, feel free to drop it there, or if you would have a question later on, email me or message me on Twitter, and I will try to, I will do my best to answer it. But for now, we have like 45 minutes left. So let's wrap it up by talking a little bit about maps and tables. And then I will try to give you as much inspiration as possible if you want to see more great examples of data visualization or learn more about it. So maps and tables are a little bit different kind of chart types, of course. Maps, first of all, yeah, I don't know exactly why, but people are automatically drawn to maps, and maps work really great. If you're doing some kind of research and there's some kind of geographical spatial information involved, by all means, create a map and put it as a centerpiece on your scientific paper, for example. Like here in this case, it draws the attention. It works very well, and also it's worked really well at explaining the story that's going on. There's been a lot in this specific example. There's been a lot of thought put into creating this map. If we zoom in a little bit, so even without reading the text, just looking at the pictures and looking at the map, and maybe reading the title, we know that we're talking about lions here. We see this map of Africa, and the title says or hints that we're talking about genetic diversity of lions. And by cleverly designing this map, if I just look at this map without any prior knowledge, I see that there are two regions. So one region is indicated with a solid line, and another region is indicated with a dotted line. And so there are two regions on top and the bottom. Combined with the picture of the lion and the title, I would conclude that, oh, maybe there are two different genetic groups of lions in Africa. One is more in South and Eastern Africa, and one is more in Northern and Western Africa. And indeed, if you read the entire text, you will come to the same conclusions, or you will find that this conclusion is correct. But only, yeah, reading this entire text will take you maybe 15, 20 minutes. Looking at the map just takes you 30 seconds, and you will arrive at the same and accurate conclusion. So this person who has created this scientific poster has spent a lot of time thinking about how to create this map, and it really works in this case. But unfortunately, maps are pretty difficult to work with, because it's very easy to create maps that distort the message that we are actually trying to convey. It's easy to create maps that don't really work the way that we intended them to work, or maybe they do what we intend them to do, but it's not really a realistic image, or it's not really correct, or we are actually cheating a little bit, or it's difficult to extract the information that we want to extract from a map. And especially, for example, population density is something that regularly pops up, and that completely makes makes maps very difficult to interpret. Let's get back at one of the maps that we saw earlier. So the map of coronavirus cases, but this is still at the end of March, in different countries throughout Europe. And of course, these are absolute numbers, so the sizes of the bubbles are scaled according to the number of cases, and then you can immediately see that, okay, in Italy, Spain, Germany, and France, those are really the countries with a lot of infections. But it's difficult to compare if you, for example, look at the circle of Luxembourg. The circle of Luxembourg is pretty small, but it's not very tiny either. So if you want to compare the circle size of Luxembourg with the circle size of let's say Poland, so they are both almost equal in size. So the number of cases in Luxembourg and the number of cases in Poland is roughly about the same. But we, of course, know, we have some prior knowledge that in Luxembourg there are much fewer people, much fewer inhabitants than there are in Poland. So if we have to calculate a little bit in our head to understand that, okay, in Luxembourg, the situation is much worse than in Poland because there's the same number of cases, but there's a lot less people in Luxembourg than there are in Poland. But this information is not in this map. We have to already know it if we want to draw the right conclusions. And if we don't know all this information, then I suppose that we don't know all the population numbers for each of these different countries. And it's actually difficult to say something about how bad the situation actually is. So that's why this is a map from the Washington Post, and the Washington Post has now changed to a different kind of map. Well, it's still a bubble map. This is a world map, but it amounts basically to the same thing. And here you can choose at the top, so it's a kind of an interactive map. And here at the top, you can choose if you look at the total amount of cases or if you look at the number of cases adjusted for population. So the adjusted for population is often a better choice because then you won't have that problem. And like we had, that you have to know the numbers of people living in each country. You don't need to know this prior information. But there's another problem then. Both situations are not ideal, and that's why data visualization is often more complex than it looks at first sight. But you could think like, oh, now we have adjusted for population, our problem is solved. I will immediately go to the comment in the chat, but let me first finish this. So you could think, oh, we have adjusted for population, the problem is solved, but then you get some weird data artifacts. Like, for example, if you look at, there's a very large bubble here on this chart on the border between Spain and France. I suppose that's Andorra. And in Andorra, there's a huge number of cases per 100,000 inhabitants. But that's simply because in Andorra, there almost nobody lives there. I don't know how many people live in Andorra, but maybe 1,000 or a few thousand. So if there are just a few cases there, it immediately is a huge number of cases per 100,000 population. Here in Belgium, we have a very small town, which is called, it's the best town here in Belgium on the coronavirus because they have no infection at all. But it's just 80 people living in that town. So it doesn't really mean anything. And as soon as they would have one infection, that's one person out of 80 people, it would go to, wow, over 1,250 cases per 100,000 inhabitants, but that doesn't really mean anything. So it's not that by adjusting for population, we have solved the problem that this original map had. So now we can go to the comment on the chat. And yeah, it's interesting to put it in relation of number of tests. Yeah, definitely true. So the positivity rate of tests that you're doing, so the number of tests and the fraction of tests which come out as positive. But then again, that's maybe still not enough, because then you have to know, okay, who are we actually testing? Because here in Belgium, you can get tested for two reasons. Um, One reason is if you're feeling sick and you want to get tested, then you can get tested. Or if you are traveling to a country where you need a test to go there, then you can also get tested. But you need then information about how big are these two groups of people that we are testing, because people you are testing because they feel sick, they will have a much higher positivity rate than people you are testing because they are going to travel abroad. Um, and then if these groups are 50-50, the same size, then we can know a little bit about what's going on. But if 95% of the people that we are testing because they feel sick, we will have a very high positivity rate. But if we are testing them because they're going abroad, we will have a very low positivity rate. So all these kinds of questions are really great and have been the subject of lots and lots of debate over the past few months on data science, so data analytics and data science in general, but they all are reflected in the data visualization and in the way we visualize the data. And don't be fooled into thinking that data visualization is always objective, because it is absolutely not. The way that we have to make so many choices in order to turn our raw data into the raw data in itself is not really objective or completely objective, and then we still have to make additional choices on how are we going to visualize it, which visual variables are we going to use, which colors are we going to use, and etc. etc. Um, so it makes it even more subjective. Not that that's really a problem, but you have to be aware of it, that data visualization will never be fully objective. If you want to know more about or yeah, learn more about data visualization in about the coronavirus, then there's one person you should really follow. Is John Byrne Murdoch, who is the data visualizer at the Financial Times. He's on Twitter and he's tweeting a lot about they are doing great things with data visualization, especially working with lots of small multiples. And with showing trends. And he was also a big proponent of using logarithmic scales, for example, which was not logarithmic scales for the vertical axis, which was not something that was commonly done in newspapers, especially because the general public tends not really to know how they have to interpret logarithmic scales, so it requires some additional explanation. But they did some analysis and they concluded that it was worth going to this a little bit more complex way of visualizing data with some additional explanation to the audience on how to interpret it, because that would give rise to better comparisons between the different countries. So it was a balance between putting a little bit more effort into the hands of the audience, because they had to learn something new and have to learn some way how to interpret something new that they didn't really see before. But on the other hand, they could understand the story and the message behind the data better. So John Byrne Murdoch at the Financial Times. And this is another example of how it can sometimes go wrong if we're showing maps without thinking about it. Another reason why I don't really like, no, that's not true. This has not really anything to do with choropleth maps, but this is a map that Donald Trump once tweeted to show, like, look at how many people have voted for me, because almost the entire country of the United States is colored in red. So red are people or counties that voted majority for Republicans, and blue are the counties that voted for the Democrats with Hillary Clinton. And he showed this map to see, look, how enormous that my victory was. But this is of course completely distorted, because we know that the blue here is a little bit around the large cities, New York, etc., at the East Coast, and also at the West Coast, where you have Los Angeles and San Francisco. There's also there are the main blue areas, but coincides with just areas where many people live, like maybe nearly 50% of people in the United States live at either the East Coast or the West Coast. But we need to know this information in order to correctly interpret this map. So that's this map in itself is not really showing enough information. And there are some approaches then that other people are taking in order to make it more clear, or to give a more realistic or truthful visualization of the election results. For example, you could add, so basically they all amount to, we will add additional visual variables to our data visualization in order to show this population density aspect that was missing in the original map. So here we are just we are turning to dots rather than a choropleth map. This we are showing more dots if more people are living in a certain state, for example. And then you can see that the big states like California, Florida, Texas, New York, that they just put more weight in the balance than smaller states in the middle, like with Wyoming or Montana or North and South Dakota, for example. So here, looking at the dots, we immediately get a much more nuanced view. It's maybe not as pretty, or it's maybe not as impactful, but it is more correct. An alternative approach is by using value, again, value as an additional visual variable, where sparsely populated places simply have a very low value, so that they're almost white and difficult to see. And then areas where lots of people live, they will have much darker colors, so darker blue or darker red, for example, in this case. And then again, this gives a more nuanced way of showing the data, and it actually gives also a nice way of representing where population in the United States is actually living. And a final approach to solve this is what's called a cartogram. The cartogram might look a little bit weird if you see it for the first time, but in a cartogram, the approach is that you take the shape of the country or the state or the whatever that you want to represent, and you scale it. So you use scale as an additional visual variable, and you scale it according to the number of people living there. So you take this additional parameter and you take this additional visual variable. But in a cartogram, it's done algorithmically, so that the states that originally are together, they also stay together. So you're shrinking the entire country a little bit, or you're blowing up the states where lots of people live, and you're shrinking the states where only few people live. And then you get a kind of distorted image of the United States. It's still a little bit recognizable because, you can still see the shape of Florida and the shape of Connecticut, etc., New York. But because there are a lot of people living, they are embiggened compared to, for example, Alaska, which is now tiny on this map. And then if you color the states in, you have this additional size variable, which accounts for the population in each of these states. And in this way, it also gives a more balanced visualization of the result. So all these three approaches have in common that we just have to introduce additional visual variables in order to make this map easy to interpret. Just a final example to show that, I make the same mistakes. So even when I'm aware of that problem with maps, I will still make the same mistake. For example, this is a map of one of the original visualizations which I made for my visual about the Nobel Prize in Physics. And I put an orange dot for each birthplace of a Nobel Prize in Physics laureate. And then you can see that there's a large concentration of people in around New York. 17 laureates were born in New York. There's a lot of people from Europe, and then you have a few from Japan, and that's about it. So this learns us something, that yeah, people winning the Nobel Prize in physics are usually people from Western countries, but it's completely distorted also, this image, because we have to know information. Yeah, obviously there are also, maybe there are more people living in the East Coast in the United States, and there are a lot of people living in Japan. And of course, in Africa, there's just like two Nobel Prize in physics winners in Africa. But we have to know, okay, how many people are actually living in Africa to make a conclusion of, is this a lot or is this a little? And to even further complicate matter, yeah, the Nobel Prize has been awarded for 120 years now. So population density was completely different in 1900. It was completely different in 1950, and it's completely different compared to the situation now. So actually, a map looks nice in a data visualization here, but it's actually a really poor choice to visualize the data, because there's so much additional information that we need to know, or that we expect our audience to know, in order to extract the correct conclusion from it. But yeah, it's our audience cannot simply know all this information in their head. Um, Al Abdirahmani is asking which visualization tool I use. I will go into more detail next session, but for in this case, for example, this was made in Adobe Illustrator, which is more a design tool than a visualization tool. I should think about how I put the dots. This is from a few years ago, so I think I didn't knew a lot about how to create accurate maps. I must admit, a little bit ashamed, I think, but I think I put the dots on here manually. It's like 200 dots, so that's still a little bit manageable. And then I do most of the work in for the data visuals, in this case in Illustrator, because I'm a little bit of a freak and I want to have everything in exactly the position that I want it, and in exactly the color that I want it, and I want the labels in exactly the place and the font that I want them. So this is the finishing up is done in Illustrator. But usually there are like 3 steps. We will see it next time. So, but the first step is extracting the data that you actually need. So you will have usually a large data set, and you extract just the data that you need for the visual. Then you use a kind of tool. Sometimes it's just Excel, sometimes it's an online tool, sometimes it's something more complicated that you have to code to create the visual, the basic visual that you want. And then I use a third tool, in this case Illustrator, to pimp the design, because the default graph that comes out of Excel is usually not pretty enough. You can do a few things in Excel to make it prettier, but most of the work is then done in Illustrator, or there are alternative approaches that we go into next week to clean up the design. And then finally, we have talked a lot about charts now and a lot about data visuals, and maybe this is not technically data visualization, but I want to include it because it's a question that I always try to ask to my clients. If a client comes to me and they want to create a data visual, one of the questions that I always try to ask is, do we actually really need a chart in this case? I will give a concrete example from one of my clients who was a fintech startup, and they created an application, a smartphone application, to manage your investment portfolio, and especially to do simulations on how your investment portfolio would evolve in the coming years. So the first screens that we made were like this, with lots of sliders and then a very elaborate chart with the line showing how your money would evolve and how the variation about it, and what it would do, like when it was better than expected and worse than expected. And then you could scroll like, do I want to know it in 5 years or 10 years or 20 years, and click on different things and use your finger to slide and get all this information. And then we realized that we were actually putting way too much information and way too much details on this graph, and actually just creating noise rather than creating relevant information. And then we took a step back, tried to think of our audience, people doing simulations about their investment portfolio, and try to think, okay, what do they actually want to know at the moment they're doing a simulation? What do they want to know? And what they actually want to know is, okay, I put this money in now. How much money will I have in 10 years? So we completely simplified the visual and just showed a number. Actually, with a very basic chart. You could go even more extreme and simply just show the number, like, okay, if you put in this money now and every month an additional 250 euros, then in 10 years you will have exactly this amount of money. And that's all that these people want to know. How much money will I have in 10 years? They don't need to know the evolution between now and in 10 years. They don't need to see visualizations of the uncertainty. They don't need to slide and use interactivity. All they want to know in order to make the decision at that time is the number. So that way we opted, let's just not make a chart, definitely not a complicated one, and let's just show the number. A number is instead of a chart is maybe a little bit very extreme, but in many cases you could also, instead of resorting to chart or having to create complicated charts, maybe just showing a table is also a valid option. And a table can be less boring than it sounds initially, because you can add a lot of additional annotations and pointers to make a table easier to interpret. For example, in this table, values are colored according to whether they're positive or negative, or are they larger or smaller than a certain average. They even have different values, so you can see that there's darker green and there's lighter green. There are small icons to show, okay, which party here are we talking about. Things that you can do, or making text bold, or making text softer in color in order to make tables easier to interpret and easier for your reader. Nowadays in Excel, you can create spark lines, or you can introduce small visuals into rows so that you can have a table like this with logos of companies, also with spark lines, so you can quickly see how things are evolving. These are all tricks to create data tables that are not boring to look at and that make it easy to interpret what's going on. And I have even seen for the coronavirus a great example where people were introducing small heat maps into rows of a data table. In this case, it's a kind of one-dimensional heat map showing an evolution over time, but it really works quite well here, I think. Just some rules, points of advice if you're designing data tables. The link here, if you click on the link on the bottom of this slide, will take you to a very interesting article on the Data Wrapper website, a blog post with lots of tips and advice on creating data tables that work for your audience. For example, here are 4 different ways that you can style your different rows. Which borders should I use? Maybe only the horizontal borders. Maybe I can use some like zebra striping, where the odd rows are a little bit gray and the even rows are white. Makes it easier for people to look up the data in the table. Maybe I shouldn't use borders at all. Things like that is all discussed in this article. Similarly, you can give additional pointers to people, make it easier to interpret. For example, in the top left example, there's a row which is colored gray because it's the summary of all the other rows. And by coloring it the background gray, it immediately makes it clear that this row is different from all the other rows. Or in the top right, the cells are again colored depending on the value which is in them. Then two basic guidelines or rules of thumb are in the bottom left. You can see that think about the font that you are choosing for your data table, because there are 2 different kinds of fonts. There are fonts where proportional or tabular fonts, and this only applies to this mainly applies to the numbers. And it will impact if you put different numbers below each other, will they take up the same width or not? Because in a tabular font, each letter, each glyph has the same width. And then if you have a number with nine figures in it, it will always have the same width. And if you have a large table with many numbers below each other, it's much easier to compare if you're using a tabular font compared to a proportional font. That's one rule of thumb. The second rule of thumb is illustrated at the bottom right, is just provide enough padding or white space around the text and around the data. You can rarely do wrong by providing a little bit more space to breathe. Makes it much easier for the viewer to read. If you have a table where all the data is cramped up together, you will already be disgusted beforehand, and you will not be very happy if you have to delve into that data and try to extract information from it. And if you foresee enough white space, enough padding, enough row height, then it will be much easier for people looking at it. That brings me to some inspiration, I think right on time. It's 12 o'clock, so I think we all start looking forward to our lunch. Some inspiration. So if you have time, maybe this afternoon or this weekend, and you want to learn more about data visualization, or you want to see more examples, where do I usually go? Because just as a disclaimer, I do not have a training in or a proper training in data visualization. I learn most of what I do from things that I see and that I see other people do. I'm pretty active on Twitter, so I'm following a few interesting people, data visualizers who are on Twitter. There are too many to mention, but I have my own list of people who are very active in the field of both data visualization and creation of infographics. Some of them that I really look up to and really look forward to them posting about new work that they are creating. If you also want to or just have a look at this list and see who's on there, feel free to check it out. It's a public list. And then that's just it's for me it's more interesting than seeing everyone complain or seeing constantly political things appear on my timeline. I have a timeline with only people talking about data visualization and beautiful infographics. There are a lot of books that you can read if you're interested into data visualization. Some of them, as you can see, are highly recommended, especially that's for you as a researcher. I try to think, okay, what could be interesting for you. Coincidentally, I have some of them here. So this is the Trees, Maps, and Theorems by Jean-Luc Dumont. I have mentioned Jean-Luc Dumont earlier because he does a lot of work on scientific communication and effective scientific communication. So which rules should you follow to make sure that your communication is as effective as possible, both if you're giving oral presentations, if you're writing an article, if you're creating a poster. But there's also an entire chapter on data visualization or creating charts for use in articles, for example, and how to avoid noise, how to make charts as easy as possible to interpret. That's one book that I really recommend. And then there's another one. If you personally feel completely not confident about data visualization, or you feel like you're still a beginner, and then I would advise Storytelling with Data by Cole Nussbaumer-Knaflich, a woman who used to work at Google. Now she has her own consulting firm with many people giving advice on data visualization. And her book is very practical because it's aimed at people who work in a professional setting but don't really have experience with using specific tools or specific software. So it works a lot with examples that you can do in simply in Excel or in PowerPoint, with some techniques about which colors should I choose, which things should I highlight, how should I make annotations, how should I do my labeling, how should I do my legends, etc., is explained in this book. She also has a very interesting blog. If you don't want to spend money on a book, you can go to the blog, and she has lots of information and examples and tips and tricks there. I think the next slide is about blogs. Yes, so yeah, her blog is even not on there, but if you Google storytelling with data, you will find her blog. There are some other blogs like Visualizing Data is from the same guy who had the Chartmaker directory. And Chartable is another very highly recommended blog with lots of articles. For example, an article on which colors should I choose for my chart or for my map, depending on what I try to do. We will talk more about colors next session, but they have really they have in-depth articles with great advice and advice which is often scientifically supported, or it's not from a design approach usually, but it's from a combined analytical and design approach that they look at data visualization. So each article that appears there, I like to read it as quickly as possible because it's always very interesting. And then finally, if you like watching videos or you're having lunch and you want to watch something on YouTube at the same time, there are a lot of interesting videos online. But what I especially can recommend is the DataFest YouTube channel, which was DataFest is a data visualization conference, which usually is in Tbilisi in Georgia. So very few people can go to it because it's pretty far away and difficult to reach. But now, due to Corona, everything had been moved online. It was very easy to get access online. And what they've also done is recording all the sessions, and they have put 23 different talks by really experts in the world, experts in the field of data visualization, and they put them online on YouTube and made them freely available. So that's quite mind-blowing. I think that there are now 23 different talks freely available for you to watch and to learn about data visualization and to be amazed and by all these examples and things going on. There are also a few podcasts about data visualization, but even though I'm a big podcast fan, I don't think there's no one recommended here. As you can see, that's because I'm a big fan of podcasts, but for me, it doesn't really work for visual things because it's difficult. You can listen to people talk about a data visual, but if you can't see the data visual yourself, that's pretty dumb, or pretty difficult, in my opinion. So that rounds up the session for today, and brings me back to the homework assignment that we're going to do. So Wednesday, I already said, have a look at one of the three data sets that I shared and play around a little bit with it, try to get familiar and try to see if you can extract some key messages from it. That's maybe something interesting that I would like to make a data visual about. So now if you want to take a step further in your homework assignment, what I would advise you to do, we have talked about different kind of chart types, and we have also have given you some inspiration and also some websites where you can learn more about these different chart types. Take maybe the key messages that you have written down from the past assignment, take them with you, and try to explore some different concepts on how you would turn this into a data visual. And again, don't stress out about it, or don't worry too much about it. This can be very simple, and for that reason, I have included just 2 examples that I once made. It's just a basic sketch of how could a data visual look like, and it doesn't have to be complicated. But for example, the left one is, okay, I want to use a waffle chart to visualize this this data that 1 out of 5 non-investors believe, blah blah blah. So I think, how would it look like if I used a waffle chart? I drew 100 small squares and filled 22 of them. And just that's my concept sketch for creating a data visual. Or the one on the right is a very simple like stacked bar chart, which amounts up to 100%. Could also be replaced by pie charts, but I thought here maybe a stacked bar chart would work better because we would need some annotations next to it, etc., in order to tell the story and to make sure that the message reaches the audience. So that we can move to the next stage of the homework assignment, it would be nice if you take your key messages again, combine it with what we have seen and what you can find on the internet of different kinds of data visuals and chart types, and come up with 2 or 3 concept sketches. And then the next session will be on practical turning a concept or a data into an actual visual, and what tools can you use for it and what software can you use for it. And then the homework assignment will be to take one of these 2 or 3 concept sketches and turn it into an actual visual that we will then discuss and give feedback on Friday. So that wraps up the session for me. We're 5 minutes earlier, but I don't think that's a bad thing. We can have lunch 5 minutes earlier. I thank you for listening. I have done a lot of talking again. I think I can feel it in my throat. I hope you're enjoying. You will have a nice weekend, and we will see each other again next Wednesday at 2 o'clock in the afternoon. So thanks for watching. And if you have any questions, send me a mail or send me a Twitter message. Goodbye. Welcome. You're all too kind.